Bismillahirrahmanirrahim. In this unit, we will introduce some fundamental terminology related to MOSFET physics and device modeling, such as C oxide, capacitance of oxide layer, CD, depletion layer capacitance, T oxide, thickness of oxide layer, TSI, depletion layer thickness, epsilon oxide, dielectric constant of oxide layer, epsilon D, dielectric constant of depletion layer, capacitance ratio, and bulk charge factor. Firstly, we discuss about capacitance of oxide layer. This refers to the capacitance associated with the oxide layer in MOSFET device, typically used between gate and channel, and it affects the device ability to store charge and influences the threshold voltage. Similarly, CD is used to represent depletion layer capacitance, and this is the capacitance of the depletion layer in the semiconductor, which occurs when a p-n junction is formed and charge carriers are depleted in the region of near the junction. CD play a vital role in determining the electrical characteristic of diode and transistor, impact their behavior under various biases. T oxide is referred as a thickness of oxide layer, and it is the physical thickness of the insulating oxide layer in semiconductor MOSFET device. The thickness influences the device capacitance as well as threshold voltage, affecting the overall performance and scaling of MOSFET. TSI, depletion layer thickness. This is the width of the depletion layer region in semiconductor. And this width affect the electrical field and as well as the charge distribution, which are very crucial for device operation and performance. Epsilon oxide is a dielectric constant oxide layer, and this parameter represents the ability of oxide material to store electrical charge in the form of energy and in electric field. A higher dielectric constant can lead to increased capacity, which is beneficial for device performance. Epsilon D, dielectric constant of depletion layer, and this is the dielectric constant associated with the depletion region of semiconductor. It influences the overall capacitance as well as the electric field distribution in the depletion layer of MOS. Now we discuss about capacitance ratio. The capacitance ratio can be defined as alpha, which is equal to the C oxide divided by CD, and their typical value is 1 by 3, and typical value is 0.333, and so on. Importance of capacitance ratio, as usual, at higher capacitance ratio, indicate that the gate capacitance is significantly larger than the depletion capacity, which can lead to the faster switching time and improved device performance. Similarly, threshold voltage, the capacitance ratio also affects the threshold voltage of the MOS. A higher C oxide relative to depletion capacitance can lead the threshold voltage with making the device more sensitive to the gate voltage changes. Now we discuss the effect of the charge ratio on the capacitance ratio on the charge storage. The capacitance ratio influences how effectively the MOSFET can store charge, which is critical in dynamic application like digital circuit and some advanced analog and mixed IC circuits. Scaling as devices are scaled down in size, maintaining a potential optimal capacitance ratio become important for ensuring reliable operation and performance. Understanding the capacitance ratio in MOSFET is very crucial for the design and optimizing the modern electronic devices. and VLSI circuits, impacting speed, efficiency, and overall performance. Now we discuss about bulk charge factor. Bulk charge factor can be defined as the 1 plus alpha and as the ratio of charge in the bulk of the semiconductor to the charge in the channel region. It is often denoted by a symbol N and play a significant role in determining the electrical characteristic of MOSFET under certain environment and operations. N is typically around 1.3 to 1.4. It is acceptable at the beginning of the modeling to simplify assume N is equal to 1. However, including N in the equation significantly improve the accuracy and efficiency, which we will discuss in later stage.